Usually there's a point like pause. Yeah, if you ever watch
I think it froze. It's thinking. No, it still says, here we are, greetings and welcome. And that was like, it just jumped from like 2 seconds to 10 seconds. Perhaps it's possible there was a time freeze or some sort of time warp. It's difficult to determine. But either way, today, greetings and welcome to you, whichever time period you might be existing in. We're talking about powers and roots of complex nombres. Nombres, that's right. Here we've got a little derivation for you. We're going to derive this. And one way I could calculate, whoa, don't want to spoil too much there. So squaring, for instance, a complex number is the same as multiplying it by itself. I'm sure you guys would agree. And I'd get r times r is r squared. I think you guys would agree. And we've seen this foliage before, not to be confused with foliage, in which when I FOIL this all out, I end up getting two separate sum identities for both cosine and sine, if you remember your trigonometric identities. So as the result of foiling this out and skipping a bunch of work, you end up getting cos theta plus theta and I sine theta plus theta. All right, and now you might realize, wait, theta plus theta, those are like terms. Those are like terms. That's what they're like. And so theta plus theta is 2 theta, and theta plus theta over here is also 2 theta. So now notice, there it turns out there's a relationship between this two, this two, this two, and they all link back to this two. What? So oddly enough, if I unevened this problem and made it an odd, like a 3, that then all of these would become 3s. And if I fourthed this, then all of those would become 4s. And this is the essence of what my good friend de Moivre tells us. So this is, yeah, actually, if you wouldn't mind, Tristan, just giving us a correct pronunciation.
De Moivre.
There we go. That guy's theorem. From this point on, referred to as de Moivre's. This is what his theorem says. He says that if you have r cos theta, I sine theta, and you raise it to the nth power, that is the same as r to the nth. So my new modulus is just the nth power of my original modulus. And my new amplitude is just n times the original amplitude. How wonderful. What wonderful weather we're having. So let's do a little example of this. I'm trying to throw the people on the internet off from where we live because my saying what wonderful weather we're having, the fact that it's a terribly cold, rainy, sleety day, would then they wouldn't suspect to look in this particular region of the United States.
You said
Cancel it.
So, right, because they would have known that there was a storm brewing over us right now.
Good thing they know that now.
So yeah. So let's use some de Moivre's here, and let's find the value of 2 plus 2 roots of 3i to the 6th power, which, if this is currently rectangular in its form, and if I wanted to do this, I would actually have to write out that times that times that times that times that, like six times, and then foiled, and then taken that answer and distributed, and then taken that answer and then distributed, and then taken that answer and then distributed. And it would have been terrible. But de Moivre, he's like the microwave of being able to do the power of a complex number. He'll cut your time down way in less than half. I didn't know how to end that sentence there. Also, disclaimer, this teacher is currently using cold medication and my brain is all stupefied. Not recreationally, but medicationally is what we called it, yes. So thank you for your grace. Cutting me some slack. So here we go. first thing I've got to do, let's convert this to polar form. So I happen to know that my a is the 2 and the b is the 2 roots of 3. And you guys, you've done classic polar form so many times. So r is going to equal the square root of 2 squared is 4 plus 2 roots of 3 all squared. 2 squared is 4, root 3 squared is 3. So that's 12. Well, what do you know? Oh, hey, what do you know? R is equal to 4, right? And you've seen that before. And let's see, I can do some theta. I'm going to use my clever arctan version 1. Arctan. I was just thinking of arctan as the name of an individual, and then I was thinking of Never-Ending Story, but that was Atreyu, right? And what was like I can't remember. D'Artagnan, there it is. Wow. That was from the Three Musketeers?
Yep.
He's the funny one.
I can't remember the name of the kid then from Never-Ending Story. So anyways,
Cold medicine.
yeah, I'll blame it on that. But no, Never-Ending Story is a completely different story. There's also like a Snuffleupagus, that's a flying dragon in that one. So here we go. Theta is equal to arctan of that is the same as, right, the tan inverse of just plain old root 3. And notice I don't have the plus pi here. Why? Because the value of a was positive is what I'm doing. And tan inverse of root 3, when does that occur? Is that 60 degrees? I think it is. Or pi over 3? I think so, yeah. Seems to make sense to me. So that means this is the same as 4 times the cosine I sine of pi over 3, all to the 6th power. So if I want to analyze this situation, that means not only is r equal to 4 and theta equal to pi over 3, but what letter does he use? He used n. That's a shame. That's fine, though. I think I should have used p for that, but that's fine. Let me verify, actually. Verify. Verification. Making the math more accurate. No, they used n's in the book, but I don't know what De Moivre is doing. He's probably rolling over in his grave. It should have been a p. So I'll call it n for now. N is equal to 6. And what am I going to do? I'm just going to plug it into this thing right here. Recognize this? So I've got r to the n times the cosine of n theta plus I times sine n theta. Right? So that's what I'm going to just plug the r, theta, and n in for, and it will tell me the power. So I'll have r is 4 to the 6th times the cosine of n theta. So that's 6 times pi over 3. I guess I'll write that out. Why not, shall we? 6 times pi over 3 plus I times sine of 6 times pi over 3. And close that double parentheses. 4 to the 6th power. I don't know what that is. 4096. I should have known that one. Cosine of 2 pi plus I times the sine of 2 pi, right? Because 6 and 3 reduce. You guys are all master fractionites. Fractionites? Yeah, that's good. We'll call you that. And what is cosine of 2 pi? Well, that's the same as cosine of 0, which is?
You got it.
1.
Is it a negative one?
2 pi is...
One.
Oh, okay.
Okay.
Going down.
Well, and sine of 2 pi is 0. Nope, I just wrote theta instead of 0. But also, this I needs a little tail on it. There it is. And I times 0 is 0, so this is just 4096. So, what do you know? Raising that complex number to that power is just 4096. Which, actually, interestingly enough, remember that I to even powers actually gives us real numbers. I to odd powers will give us I powers. Now my brain's just running with that right now. Thinking of like X-ray vision would be an I power. But anyways, I digress. Check out this guy. Actually, meh. I'm gonna, yeah.
Oh, I was
That
like
was
triangle.
awful.
I'm gonna change this example on the fly here, guys. Here we go. Let's pretend I've got 2 times cosine of pi over 6 plus I times sine of pi over 6. And let's say I'm raising this all to the negative 5th power. I just changed it up on us because originally I had a rectangular form, and I'm sick of converting from rectangular to polar. I think you guys are masters at it. So I'm just going to cut that step out the way. So, looking at this, could you tell me what is the value of r, theta, and n de Moivre? -5. So, oddly enough, this will work with negative exponents. Isn't that special? So, so I'll have 2 to the negative 5th power multiplied by cosine of -5 times pi over 6 plus I times the sine of -5 pi over 6. -5 times pi over 6. That would be very... No, actually, that's exactly the same thing. My apologies. 2 to the negative 5th is the same as 1 over 2 to the positive 5th, which I think you guys realize is 32. And cosine of -5 pi over 6 is right there. So the reference angle, as de Moivre would pronounce it, is pi over 6. And it's in this quadrant. And I've got the snifflies. Sorry. And both sine and cosine are negative in that quadrant there. So let's rewrite these reference angles wise. So cosine is now negative cosine of pi over 6 plus I times the negative sine of pi over 6. And look at this, I've got like the classic triple close parentheses there. I love it. It looks like you've got like a good Wi-Fi signal almost or something, like, right? No? That's what I think of when I see that. So 1/32 multiplied by, what is negative cosine pi over 6? Negative root 3 over 2 plus, no, minus 1/2 I. And now I can just multiply those denominators by 32 essentially, and I get negative square root of 3 over 64 minus 1/64 I. And there we go. I was just able to raise that to a negative exponent, the 5th power. Good times.
So up here, you just find wherever theta is, and then you see if it's negative or positive in there, and that changes the negative and positive of sine, cosine.
Good. We're in it.
We're not.
Yeah, the positive negative is based on the quadrant and the reference angle. Yep. So let's consider this. Here's another discovery. No, I'll call it, no, it's a discovery. We'll discover this rather than derive it. Because you guys, you don't even know where we're going with this, so it's a discovery to you. I know where we're going, maybe.
Ooh, ignorant.
So don't write this down. But if I have 1 over p,
Why is that one P?
I know, that's what I'm saying.
We take it to N.
No, actually, this one, we'll use n later on. oddly enough.
But they're the same?
Nope,
No, they're different now.
they're different now.
What?
De Moivre will tell you. So if I raise it to a fractional exponent, which, by the way, a fractional exponent is also a type of a root. So this is the same as the pth root of that whole thing. The value of n would be 1 over p, and I just plug it in like so, and then n times theta is now theta over p, and right like that. So I could actually use this if I wanted to calculate this with a fractional exponent. It still works. And it says when finding a principal root, the interval negative pi to positive pi is used.
What is a principal root?
What is a principal root? A little recall sideline note coming at you. A principal root, if I ask what the square root of 4 is, the principal root is 2. The non-principal root is the negative 2.
Oh, okay.
I don't remember if those had a name. The other guy. But so the principal root was the positive one in that case.
Oh, I understand.
So that's what we mean by principal root. And I do believe that actually that is the correct spelling of principal, by the way, which you would not have expected in a Mr. Waddy lesson. So you're welcome. Oh yeah, that's definitely the right spelling. That's what I thought. That's what you get for thinking. So take that, friend. No, I might have pointed at a student. That's okay though. Sometimes, I mean, it's okay.
Yeah, your example boxes are pretty terrible.
Yeah, you're off your game today.
Hey,
So we don't have to.
let's write down this this thing right here.
Is that a formula we need?
No, it's just the same thing that it's just indicating that you can have a fractional exponent and use this De Moivre. De Moivre will still help you out,
Alright.
is all that was. So if I want the cubed root of 8i, this is the same as 8i to the 1/3 power, right? And 8i is currently in rectangular form, in which, what is the value of a and what is the value of b?
A is 1. B is 8.
Is it 0? Nah.
A plus bi? Right? Okay, it's okay. We all went down that road for some reason. I don't know why, but that's fine. So let's rectangularize it. Actually, I might be able to figure that out. Oh yeah. Guys, let's graphically rectangularize. No, polarize this. Well, think about this. Going left and right 0 and then up 8 is the point right there. What angle would this be? Or pi over 4? Nope. 2. And what distance would this be? 8. So that means my modulus is also 8. So I was able to kind of like graphically figure that out, that r was equal to 8 and that theta is equal to pi over 2. So that means this is the same as 8 cosine I sine pi over 2 all to the 1/3 power.
Okay, how else do you find our theta?
This way.
Okay, yeah.
Yep. And so now I can De Moivre this. Let's. What's the value of n? 1/3. So let's just plug it in there. Really, that's what we're doing. So this is going to be 8 to the 1/3 power multiplied by cosine of pi over 2 times 1/3 plus I times the sine of 1/3 times pi over 2. Oh yeah, I know where this is going. Oh, whoop, whoop, over scrolled there. 8 to the 1/3 power is the cubed root of 8. I don't know if you know that right off the bat. Hopefully you do. That's fine. We'll work our way there. Cosine pi over 6 plus I times the sine of pi over 6. Pi over 6, of course, being a radian equivalent of 30 degrees. Cubed root of 8 is 2 times cosine pi over 6 root 3 over 2 plus I times the sine of pi over 6 is a half. So half I. And multiply by 2, I get root 3 plus I. Oh, that was like lagging there for a second there too. All right, now here we go. Just like how with real numbers, or did I talk about that a second ago? I mentioned principal roots here, right? That a square root of a number could have two answers, right? Positive and negative 2 in this case. It turns out that there are multiple roots of complex numbers, not necessarily 2 of them. So get ready for your mind to be blown. There are p distinct roots of a complex raised to the 1p power. P, yes. So what I'm saying, or I'll come back to it and I'll let you write it down after the video. So it says the p distinct roots of a complex number are the following. So there are p of them if I'm taking the pth root of something, or raising it to the 1p power. Also, look at this, curly braces, square brackets, parentheses. Isn't that just lovely? I love it. So, which I don't know if you guys realize that there was a magnitude of those. Have you known that? Oh, yeah, mathematically, mathematicians usually mathematically do that right there. So parentheses is less than a square bracket is less than a curly brace, just so you know. But I haven't been loyal to that even here. I was just double parenthesizing rather than square bracketing, but you know what's up. So,
Yeah.
what?
What comes after a curly brace?
The largest
Do you just start over?
I don't know. I don't know. Maybe it's like curly brace to the second. I don't know. That was a sad curly brace. So, so it turns out that the p individual roots, there are p of them. There's one principal one, but there are p total, can be found by replacing n in this formula with 0, 1, 2, all the way to p minus 1. Why does it stop at p minus 1 and not go all the way to p? There's p of them. So why didn't this stop at p? Anyone see it? Because
That's the distinct root.
I started counting at 0. If I started counting at 1, then I would have had to go all the way to p. But if I start counting at 0 and I still want p of them, then p minus 1 is where I'd have to stop counting. So if this was a 6th root or a 1/6 power, then I would stop counting at 5. Right? But you all start with 0. Successively, and the following equation. And basically, it's the same thing we saw earlier, except you add this 2 pi n. So you basically spin around the circle, another assumedly co-terminal angle, but it's still all over p, and n is the value here that you plug in. So we might not be able to get through a whole problem of this, but I'll do what I can. Yeah, well, think about it. I have to do this equation 3 times just to get a third root, or I mean a cubed root, right? Like if I have a 5th root, you'd have to do this 5 times.
Just do a square root.
So we have like 2 questions from
Right?
Well,
Actually, 13.
so
I'm sorry.
a equals -2, b equals -2. Let's do another graphical conversion to polar. -2, -2 is right here. This angle, does anyone know this angle? This is pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. So theta is my 5 pi over 4. And also, since this is like a 45-degree angle here, the hypotenuse of this special right triangle is the square root of 2 times longer than the other dimensions. So that means r must equal 2 square roots of 2. So you can do that. So what I'm going to do is plug this in as follows. So I'm going to have r, 2 square roots of 2, raised to the 1/3 power y 1/3 because I'm doing cubed roots, multiplied by, here's a square bracket for you, cosine of 5 pi over 4 plus 2 pi n all over 3. I guess I should have defined what my p was here too. P equals 3 based off of this guy, right? Cube roots, or the 1/3 power, if you want to think about it that way. And then plus I times the sine of the same thing. 5 pi over 4 plus 2 pi and all over 3. And what I would do is I would now evaluate this 3 separate times in which I let n equal 0, 1, and 2. And I would evaluate those 3 separate times. And in fact, if you're wondering, I could let you know. One of these is 0.37 plus 1.37i is one of them when n is 0. Then the other one is negative 1.37 minus 0.37i is another one. Yep. Okay, sorry. I was just confused by the multiple 0.37s. What's up?
So we just gotta take that and then plug.
Yeah, 0, 1, or 2 in for n,
Alright.
and
Is
that's
that always the case? Or
Yep.
just the cube root?
for cubed roots. For fifth roots, then I'd also have to plug in 3 and 4.
Gotcha.
For 10th roots, I'd have to go all the way to 9.
So it's just that equation.
Right.
Okay.
And then the third one would be 1 minus I. So it turns out that there's 3 cubed roots of that complex number. And here's a problem that I decided not to cover, but I'm going to see. Oh, it's got the blurries. I'm going to see if I can show you real quick what this looks like. Let me summarize this concept. Here we go. Ready? If I want to solve the equation x to the 5th minus 32, and I'd add 32 to both sides, and I want to solve for all of the roots in the complex plane. This is 32 plus 0i. Here it is in polar form. And then I would plug it all in, and that's what I would have. And now I'd have to plug in 0 through 4 for that, right? So I plug in 0 through 4, and I get all of these different roots in complex form. By the way, the first one was a real one. And watch what happens when I graph this. This is, I think, completely unexpected, at least by me. So there's 5 fifth roots of that number.
It's a
And
circle.
if I graph it, it's along a circle, but it actually, if you were to connect those dots, it gives you a pentagon, is what you'd end up having. So that is pretty crazy, I think. Cool stuff. So thanks for watching, Internet friends. Have a great day. Bye-bye. Don't do drugs.